Imagine a black hole 300 million light-years away, devouring a star in a cosmic feast so intense it warps space itself until suddenly, the sky blazes with a storm of superheated gas, a luminous halo spiraling outward like a dying supernova. Astronomers caught this dramatic finale in real time, witnessing the monster's indigestion as it violently expelled material at millions of miles per hour, creating a glowing ring of plasma that outshone entire galaxies. The event, powered by the black hole's relentless hunger, lasted weeks, its aftermath still rippling through space. What began as a feast turned into a cataclysmic expulsion, revealing how these cosmic beasts not only consume but also shape their surroundings, sometimes with a stomach full of stellar debris. Astronomers have witnessed a dramatic event in the distant universe. A black hole's feeding frenzy came to a sudden end, not with a quiet sigh but with a violent outburst of energy. This discovery, captured through advanced telescopes, reveals a new layer of complexity in how black holes interact with their surroundings. For years, scientists have studied black holes as voracious cosmic entities, pulling in nearby matter and radiating energy in the process. But this observation shows that their feasts don't always end gracefully. Sometimes, they end with a burst of wind so powerful it could be described as a form of cosmic indigestion. The event, which unfolded millions of light-years away, offers a rare glimpse into the dynamic and often chaotic life of a black hole. To understand what happened, we need to first consider how black holes feed. When a black hole encounters nearby material, such as gas, dust, or even a star, it begins to pull that matter into a swirling disk of superheated plasma. This process, called accretion, generates immense energy as the material heats up to millions of degrees. The light emitted during this phase can be so bright that it outshines entire galaxies. But this isn't a constant glow, instead, it's a cycle of feast and famine. Black holes don't always have a steady supply of fuel. When they do, they devour it hungrily, creating what astronomers call a feeding frenzy. However, this new observation suggests that such feasts can end abruptly, with the black hole expelling a massive amount of energy in a final, dramatic outburst. The key to this discovery lies in a phenomenon known as a tidal disruption event. When a black hole encounters a star or other massive object, its immense gravitational pull can tear the object apart. The debris from this destruction spirals into the black hole, creating a luminous accretion disk. But in this particular case, the event didn't follow the usual pattern. Instead of a steady glow, astronomers observed a sudden and intense burst of energy that lasted for weeks. This outburst wasn't just a flash of light, it was a powerful wind of gas and particles being ejected from the vicinity of the black hole. This wind, which traveled at speeds approaching the speed of light, was so intense that it could be described as a cosmic belch, a final, explosive release of energy after a prolonged period of feeding. The team of astronomers who made this discovery used a network of telescopes, including the Swift Observatory and other space-based instruments, to monitor the event. These telescopes are designed to detect sudden bursts of light across the electromagnetic spectrum, from X-rays to visible light. The data they collected revealed that the outburst wasn't a one-time event but a prolonged phenomenon that lasted for several weeks. During this time, the black hole's activity fluctuated, with periods of intense energy release followed by quieter intervals. This suggests that the process of feeding and expelling material is not a simple on-off switch but a complex interplay of forces at play around the black hole. One of the most intriguing aspects of this discovery is the role of magnetic fields in the process. As matter spirals into a black hole, it becomes highly magnetized, creating a powerful magnetic field that can influence the behavior of the surrounding plasma. In this case, the magnetic field may have played a crucial role in channeling the ejected material into a powerful wind. The wind itself is composed of charged particles that move at incredible speeds, creating a luminous trail as they interact with the surrounding space. This trail, observable in the data collected by the telescopes, provides direct evidence of the black hole's final outburst. The significance of this observation extends beyond the immediate event. It offers new insights into how black holes regulate their environment. For years, scientists have debated whether black holes are primarily destructive or if they also play a role in shaping the galaxies they inhabit. This outburst suggests that black holes are not just passive consumers of matter but active participants in the cosmic dance of energy and matter. By expelling large amounts of energy and material, they may influence the growth of stars and the formation of new galaxies. This process, known as feedback, is thought to be a critical factor in the evolution of the universe. Another important aspect of this discovery is the challenge it poses to existing models of black hole behavior. Traditionally, tidal disruption events have been studied as isolated incidents where a star is torn apart and its debris falls into the black hole. However, this observation suggests that such events can have more complex and prolonged effects. The prolonged outburst observed in this case indicates that the process of feeding and expelling material is not a simple, one-time event but a dynamic and ongoing interaction between the black hole and its surroundings. This complexity adds a new dimension to our understanding of black hole physics and highlights the need for further research into these enigmatic objects. The implications of this discovery also have practical applications for astronomy. By studying such events, scientists can gain a better understanding of the extreme conditions near black holes, which are difficult to replicate in laboratory settings. The data collected from this event could help refine models of accretion disks, magnetic fields, and the behavior of plasma in extreme gravitational environments. Additionally, the ability to detect such outbursts could improve our ability to predict and study other similar events in the future, potentially leading to new discoveries about the nature of black holes and their role in the universe. In conclusion, the observation of a black hole's feeding frenzy ending with a dramatic outburst represents a significant milestone in our understanding of these cosmic giants. It challenges existing theories, provides new insights into the complex interactions between black holes and their environments, and highlights the dynamic and often unpredictable nature of these objects. As scientists continue to study such events, they may uncover even more surprises about the behavior of black holes and their profound impact on the universe. This discovery reminds us that even in the vast emptiness of space, the cosmos is full of drama, complexity, and wonder. To witness a black hole's feeding frenzy and its dramatic conclusion, astronomers turn to a suite of powerful tools that peer into the cosmos with unparalleled precision. The first step in this discovery was capturing the black hole's activity over an extended period, requiring instruments capable of detecting faint light emissions from regions near the event horizon. The James Webb Space Telescope, JWST, with its advanced infrared sensors, played a critical role in tracking the black hole's accretion disk, the swirling disk of gas and dust that heats up as it spirals toward the event horizon. By observing the infrared glow of this disk, scientists could measure how the black hole's appetite fluctuated over time, revealing the intensity of its feeding frenzy. But infrared alone couldn't tell the full story. To understand the dynamics of the outburst, astronomers also relied on the Chandra X-ray Observatory, which detects high-energy X-rays emitted when matter is accelerated to extreme velocities near the black hole. These X-ray observations provided a complementary view of the system, highlighting the violent processes at play. Together, these telescopes allowed scientists to map the black hole's behavior across different wavelengths, creating a more complete picture of its activity. However, the most groundbreaking insight came from a different instrument altogether, the Event Horizon Telescope, EHT. This network of radio telescopes, linked by a technique called very long baseline interferometry, effectively creates a telescope the size of Earth. By capturing radio waves emitted from the black hole's shadow, the EHT revealed the structure of the accretion disk and the jet of particles that sometimes erupts from the poles of a spinning black hole. These observations were crucial in identifying the moment when the feeding frenzy abruptly ended, as the outburst disrupted the delicate balance of the system. The process began with a series of coordinated observations spanning months, during which data from multiple telescopes was collected and analyzed. Scientists had to account for the immense distances involved. This black hole lies billions of light-years away, meaning even the slightest variations in its emissions could take years to detect. The challenge was compounded by the fact that black holes are notoriously difficult to observe directly, as their immense gravity warps light and obscures their surroundings. To overcome this, astronomers used a technique called multi-wavelength astronomy, combining data from infrared, X-ray, and radio observations to build a cohesive timeline of the black hole's activity. This approach allowed them to track how the accretion disk's brightness changed over time, signaling the onset of the feeding frenzy. As the black hole consumed surrounding material, the accretion disk glowed brighter, emitting light across the electromagnetic spectrum. But the frenzy didn't last forever. At some point, the system reached a critical threshold, triggering a dramatic outburst that ejected vast amounts of energy. This event, described as a bad case of cosmic indigestion, was detected as a sudden surge in X-ray emissions, followed by a rapid decline in infrared light. The outburst itself was likely caused by a sudden release of energy as the black hole's magnetic field funneled material into powerful jets. These jets, composed of particles accelerated to near-light speeds, created a shockwave that disrupted the accretion disk, effectively ending the feeding frenzy. The timing of this outburst was critical. It had to be captured precisely to understand its impact on the surrounding environment. Scientists used sophisticated algorithms to analyze the data, searching for patterns that indicated a sudden shift in the black hole's behavior. By cross-referencing observations from different telescopes, they could pinpoint the exact moment the outburst occurred and measure its duration. This required not only advanced technology but also a deep understanding of how black holes interact with their surroundings. The process of interpreting the data was equally complex. For example, X-ray emissions from a black hole can be influenced by factors like the density of the accretion disk and the strength of the magnetic field, making it challenging to isolate the effects of the outburst. To address this, researchers used computer simulations to model the black hole's environment, comparing the predicted behavior with the observed data. These simulations helped them distinguish between natural fluctuations in the accretion disk and the sudden, dramatic changes caused by the outburst. But collaboration between different observatories was essential in this process. The JWST's infrared data provided a long-term view of the black hole's activity, while Chandra's X-ray observations captured the high-energy events that marked the end of the feeding frenzy. The EHT's radio data, meanwhile, offered insights into the structure of the accretion disk and the jet, allowing scientists to piece together the sequence of events leading to the outburst. This multifaceted approach ensured that no single observation could be taken in isolation, and that the findings were robust enough to withstand scrutiny. The timeline of the observations also played a key role in the discovery. By monitoring the black hole over an extended period, astronomers could track how its behavior evolved. The feeding frenzy likely began months before the outburst, as the accretion disk grew brighter and more active. During this phase, the black hole's gravitational pull intensified, drawing in surrounding material and creating a luminous glow that spanned across the electromagnetic spectrum. But as the system approached its peak activity, subtle changes in the data hinted at an impending shift. The outburst itself was a sudden and dramatic event, occurring over a matter of days or weeks. This rapid change meant that the observations had to be continuous and highly sensitive to capture the full extent of the phenomenon. The data collected during this period was then analyzed to determine the cause of the outburst. Scientists hypothesized that the sudden release of energy was triggered by a disruption in the accretion disk, possibly caused by a sudden influx of material or a change in the magnetic field. The outburst's aftermath was equally significant, as it left the accretion disk in a state of flux, with the surrounding environment altered by the energy released. This process, while chaotic, is a common feature of black hole activity. When a black hole consumes material, it often expels excess energy in the form of jets or winds, a phenomenon known as feedback. This feedback mechanism helps regulate the growth of the black hole by preventing it from consuming too much material at once. The outburst observed in this case was likely a manifestation of this feedback process, ensuring that the black hole's activity remained balanced. The significance of this discovery lies not only in understanding the black hole's behavior but also in its implications for the broader universe. Black holes are powerful engines in the cosmos, influencing the formation and evolution of galaxies. By studying how they regulate their own growth through outbursts, scientists gain insight into the mechanisms that shape the large-scale structure of the universe. This particular event, with its dramatic end to the feeding frenzy, serves as a vivid example of the dynamic and sometimes turbulent nature of black hole activity. The process of uncovering this event was a testament to the ingenuity of modern astronomy. It required not only cutting-edge technology but also a collaborative effort spanning multiple observatories and scientific disciplines. From the infrared glow of the accretion disk to the high-energy X-rays and radio waves, each piece of data contributed to a larger narrative of cosmic dynamics. The ability to observe such an event in real time is a remarkable achievement, offering a rare glimpse into the violent and complex processes that define black hole behavior. As scientists continue to refine their techniques and expand their observational capabilities, they will undoubtedly uncover more such events, deepening our understanding of these enigmatic objects. The discovery of this black hole's cosmic indigestion is not just a story of a single event but a reflection of the broader quest to unravel the mysteries of the universe. It reminds us that even in the most extreme environments, the forces at play are governed by the same fundamental laws of physics that shape our own world. And through the relentless pursuit of knowledge, astronomers continue to illuminate the darkest corners of the cosmos, one observation at a time. Astronomers have discovered that the feeding frenzy of a distant black hole ended with a windy outburst. This part of our deep dive into astronomers watch a black hole's feeding frenzy end with a bad case of cosmic indigestion focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For centuries, the idea of a black hole was more myth than science. Ancient Greek philosophers like Democritus and Epicurus speculated about invisible particles and forces, but it wasn't until the 17th century that Isaac Newton's laws of gravity provided a framework for understanding massive objects. Even then, the concept of a region in space from which nothing, not even light, could escape was purely theoretical. It wasn't until the 18th century that French mathematician Pierre-Simon Laplace proposed what he called a dark star, an object so massive that its gravity would trap light. Though his idea was ahead of its time, it wasn't until Einstein's theory of general relativity in 1915 that the modern concept of a black hole began to take shape. Einstein's equations showed that space and time could be warped by massive objects, and if enough mass were compressed into a small enough space, it would create a point of infinite density called a singularity, surrounded by an event horizon, a boundary beyond which nothing could escape. But for decades, black holes remained just mathematical curiosities, until the 1960s, when radio astronomy began to reveal their true nature. Astronomers discovered distant objects emitting intense radio waves, which they later realized were powered by supermassive black holes at the centers of galaxies. These objects, called active galactic nuclei, were the first clues that black holes weren't just theoretical, they were real, and they were devouring matter at an incredible rate. The next few decades saw a revolution in our understanding. In the 1970s, the discovery of stellar mass black holes through X-ray binaries confirmed that these objects existed in our own galaxy. Meanwhile, the Event Horizon Telescope, a project conceived in the 1990s, began to take shape as a way to image the event horizon of a black hole. By the 2000s, space-based observatories like the Hubble Space Telescope and the Chandra X-ray Observatory provided unprecedented views of black hole activity, revealing jets of high-energy particles and the glowing accretion disks of gas spiraling into these cosmic monsters. These observations hinted at something even more dramatic, that black holes weren't just passive consumers of matter. They were dynamic, violent systems, capable of launching powerful outflows and flares that could influence entire galaxies. The idea that a black hole's feeding frenzy could end in a dramatic outburst wasn't just a guess, it was a logical extension of what astronomers had already seen. For example, in the 1990s, researchers observed that some black holes, after a period of intense accretion, would suddenly eject vast amounts of energy in the form of winds or jets. These events, known as relativistic outflows, were thought to be a form of cosmic feedback, regulating the growth of galaxies by preventing excessive star formation. But the recent discovery of a black hole's feeding frenzy ending with a bad case of cosmic indigestion took this idea to a new level. It wasn't just about the black hole expelling material, it was about the entire process of accretion and outflow being captured in real time, providing a rare glimpse into the chaotic dance of matter around a black hole. This breakthrough wasn't possible without the decades of foundational research that preceded it. The development of X-ray astronomy in the 1960s and 1970s was critical. Instruments like the Uhuru satellite and the Einstein Observatory allowed scientists to detect the X-rays emitted by hot gas falling into black holes, confirming their existence and revealing their immense gravitational power. Later, the Chandra X-ray Observatory, launched in 1999, provided even sharper images, showing the intricate structures of accretion disks and the high-energy jets that often accompany black hole activity. These observations laid the groundwork for understanding how black holes interact with their surroundings. Similarly, radio astronomy played a key role. The discovery of quasars in the 1960s, which are powered by supermassive black holes, showed that these objects could outshine entire galaxies. The study of these quasars over the decades revealed how their luminosity changed over time, suggesting that the black holes at their centers were undergoing dramatic episodes of accretion and outflow. By the 2010s, the combination of multi-wavelength observations, X-rays, radio waves, and optical light allowed astronomers to piece together a more complete picture of black hole behavior. The Event Horizon Telescope, which began operations in 2008, was a game-changer. By linking radio telescopes around the world, it created a virtual telescope the size of Earth, capable of imaging the event horizon of a black hole for the first time. The 2019 image of the supermassive black hole in M87* was a milestone, but it also raised new questions. How do these black holes behave over time? What happens when they consume matter? These questions led to the recent discovery that a black hole's feeding frenzy could end in a dramatic outburst. The key to understanding this event lies in the history of how we've studied black holes. For decades, astronomers have relied on indirect methods to observe these objects. They've measured the motion of stars and gas around black holes, detected the X-rays emitted by accretion disks, and studied the radio waves from jets. But the recent observation of a black hole's feeding frenzy ending with a cosmic outburst was made possible by advances in technology and the ability to monitor these events over long periods. The Chandra X-ray Observatory, for example, has been continuously observing black holes for over 2 decades, allowing scientists to track changes in their behavior. Similarly, the Swift and Fermi satellites have provided real-time data on high-energy flares, helping researchers understand the dynamics of black hole accretion. The recent event, which involved a distant black hole, was likely observed using a combination of these instruments, along with ground-based telescopes and radio arrays. The fact that this event was captured in such detail is a testament to the decades of progress in observational astronomy. But the journey to this point wasn't just about technology, it was about the evolution of our scientific understanding. In the early days, black holes were considered exotic, almost fantastical objects. But as astronomers studied their effects on surrounding matter, they realized that black holes were central to the life cycles of galaxies. They regulated star formation, influenced the distribution of gas, and even shaped the structure of the universe itself. This realization shifted the focus of black hole research from theoretical curiosity to a key component of astrophysical processes. The idea that a black hole's feeding frenzy could end in a dramatic outburst was not just a new observation, it was a confirmation of long-standing theories about how these objects interact with their environments. For example, the concept of feedback in astrophysics suggests that the energy released by a black hole can heat up the surrounding gas, preventing it from cooling and forming new stars. This process is thought to be a key factor in the evolution of galaxies. The recent observation of a black hole's outburst provides direct evidence of this feedback mechanism in action. It shows that the energy released during a feeding frenzy can have far-reaching effects, influencing the growth of galaxies and the distribution of matter on cosmic scales. This discovery also highlights the importance of long-term observational campaigns. Many of the key insights into black hole behavior have come from monitoring these objects over years or even decades. For example, the study of quasars has shown that their luminosity can vary dramatically over time, indicating that the black holes at their centers are undergoing complex processes. Similarly, the recent event involving a black hole's feeding frenzy was likely the result of a prolonged observation period, allowing astronomers to capture the entire sequence of events. This underscores the value of sustained scientific inquiry and the importance of maintaining long-term observational programs. The history of black hole research is a story of incremental discoveries, each building on the last. From the theoretical predictions of Einstein to the first direct images of black holes, each milestone has expanded our understanding of these enigmatic objects. The recent observation of a black hole's feeding frenzy ending with a cosmic outburst is the latest chapter in this story, demonstrating that black holes are not just passive entities, they are dynamic, complex systems that shape the universe in profound ways. As our technology continues to advance and our observational techniques improve, we can expect to uncover even more about these cosmic giants. The study of black holes is not just about understanding the physics of extreme gravity, it's about unraveling the fundamental processes that govern the universe. And as we look to the future, the next discoveries may reveal even more about the intricate dance of matter and energy around these enigmatic objects, continuing the legacy of scientific exploration that has brought us to this moment. So, what exactly happened when this black hole's feeding frenzy came to an end? Well, the astronomers observed a dramatic outburst, a kind of cosmic belching, if you will, where the black hole expelled a vast amount of material in a powerful wind. But here's the thing, even though we've seen this event, there are still a lot of unanswered questions. For starters, scientists are still trying to figure out exactly how this outburst happened. Was it a sudden burst of energy, or did it build up over time? Some theories suggest that when a black hole stops feeding, the material around it might not just fall in, it could be violently ejected, creating this kind of cosmic indigestion. But how exactly does that process work? Is it related to the magnetic field surrounding the black hole, or is it something else entirely? These are the kinds of questions that keep researchers up at night. One big mystery is the role of magnetic fields in this process. You see, black holes are surrounded by accretion disks, swirling disks of gas and dust that spiral inward, getting heated to extreme temperatures. These disks are thought to generate powerful magnetic fields, which could play a role in launching jets of material away from the black hole. But in this case, the outburst wasn't a jet, it was a wind. So does that mean the magnetic fields were involved in a different way? Or maybe the wind wasn't caused by the same mechanisms that create jets? Scientists are still debating whether this event fits into the broader category of black hole outflows or if it's a unique phenomenon. Another question is about the energy involved. When a black hole expels material, it's not just throwing things away, it's releasing an enormous amount of energy. But how much energy was released in this case, and how does it compare to other cosmic events? For example, gamma-ray bursts are some of the most energetic explosions in the universe, but they're usually associated with the collapse of massive stars. This outburst, on the other hand, seems to be a byproduct of a black hole's feeding cycle. Yet, the exact amount of energy and the efficiency of the process, how much of the material's energy was converted into the outburst, remain unclear. Some researchers think that the energy released here could be comparable to the energy output of entire galaxies, but without precise measurements, it's hard to say. Then there's the question of timing. When did this outburst happen? Was it a sudden, short-lived event, or did it unfold over a longer period? The observations suggest that the outburst was a dramatic, rapid release of material, but the exact timeline is still under investigation. Some models predict that when a black hole stops accreting material, the surrounding disk might undergo a phase of instability, leading to a sudden ejection. But others argue that the process might be more gradual, with the wind building up over time. Without more data, it's hard to determine whether this was a one-time event or part of a recurring pattern in the black hole's behavior. There's also the issue of how common such events are. This particular black hole is part of a class of supermassive black holes, which are found at the centers of galaxies. But how often do these feeding frenzies end with such dramatic outbursts? Are they rare occurrences, or do they happen more frequently than we've observed? Some scientists believe that these outbursts might be a normal part of a black hole's life cycle, while others think they're more of an anomaly. If these events are common, they could have significant implications for our understanding of how black holes influence their host galaxies. For example, the energy released during such outbursts might affect the surrounding gas and star formation, shaping the evolution of entire galaxies. But without more observations, it's hard to say how widespread these events really are. Another layer of mystery involves the connection between the black hole's activity and the surrounding environment. When a black hole is actively feeding, it can emit powerful radiation that heats up the surrounding gas, potentially stifling star formation. But what happens when the feeding stops? Does the outburst have a cooling effect, or does it trigger new processes in the interstellar medium? Some researchers suggest that the wind from the black hole could redistribute gas and energy, creating new regions of star formation. Others argue that the outburst might simply clear away material, leaving the galaxy in a different state. These questions are crucial for understanding the broader role of black holes in galaxy evolution, but they're still far from settled. There's also the question of how we observe these events. This particular outburst was detected using a combination of telescopes that can detect different wavelengths of light, from X-rays to radio waves. But even with these advanced tools, there are limitations. For example, some of the details about the outburst structure or the exact timing of the event might be difficult to capture with current technology. Future observations, perhaps using next-generation telescopes like the James Webb Space Telescope or the Square Kilometre Array, might provide more clarity. However, until then, scientists are relying on the data they have, which means some aspects of this event might never be fully understood. Finally, there's the broader question of what this event tells us about black holes themselves. Black holes are among the most extreme objects in the universe, and their behavior can reveal fundamental truths about gravity, spacetime, and the nature of matter under extreme conditions. This outburst, with its sudden release of energy and material, challenges some of our existing models of how black holes interact with their surroundings. For example, if the wind was driven by magnetic fields, it could mean that magnetic forces play a more significant role in black hole dynamics than previously thought. Alternatively, if the outburst was caused by something else entirely, it could open up new avenues of research. Either way, this event highlights how much we still have to learn about these enigmatic objects. In the end, this black hole's feeding frenzy and its dramatic conclusion remind us that even in the vastness of space, there are still mysteries waiting to be uncovered. The outburst we observed is just one piece of a much larger puzzle, and while we've made progress in understanding it, there are still many questions that remain. As technology advances and new observations come in, we may one day have a clearer picture of what happened and why. But for now, the story of this black hole's cosmic indigestion is a testament to the enduring fascination with the universe and the endless pursuit of knowledge that drives scientific discovery. As we look ahead, the story of this black hole's dramatic feeding frenzy isn't just about what we've already observed, it's about what we're still trying to uncover. The tools of modern astronomy are already pushing the boundaries of our understanding, but the next generation of instruments promises to reveal even more about these cosmic phenomena. One of the most anticipated projects in this field is the James Webb Space Telescope, which has already begun to reshape our view of the universe. With its unparalleled ability to detect infrared light, Webb could help astronomers peer deeper into the dusty regions around black holes, where the feeding frenzy might have occurred. By analyzing the light emitted during these events, scientists might uncover new details about the dynamics of accretion disks and the mechanisms behind the outbursts. But Webb isn't the only game in town. The Event Horizon Telescope, which famously captured the first image of a black hole's event horizon, is also evolving. Future upgrades to this global network of radio telescopes could provide even sharper images of the environments around black holes, allowing researchers to study the aftermath of these outbursts in greater detail. These images might reveal subtle changes in the structure of the accretion disk or the presence of jets that were previously hidden. Meanwhile, gravitational wave observatories like LIGO and Virgo are already revolutionizing our ability to detect cosmic events. While these instruments are most famous for their detection of mergers between black holes and neutron stars, they could also provide critical insights into the chaotic processes that accompany a black hole's feeding frenzy. For instance, if the outburst was triggered by a sudden shift in the accretion disk or a collision with another object, gravitational waves might carry the fingerprints of these events. Future upgrades to these observatories, such as the Planned Laser Interferometer Space Antenna (LISA), could extend their sensitivity to lower frequency waves, potentially capturing signals from even more distant or massive events. These observations might help astronomers determine whether the outburst was a one-time occurrence or part of a larger pattern of instability around black holes. In addition to space-based observatories, ground-based radio telescopes are also playing a crucial role. The Square Kilometre Array, SKA, currently under construction, will be the largest and most sensitive radio telescope ever built. Its ability to detect faint radio signals could help astronomers track the long-term effects of the outburst, such as the dispersal of ejected material or the formation of new structures in the surrounding interstellar medium. By combining data from radio, optical, and infrared observations, scientists can build a more complete picture of the processes at play. However, the quest to understand these events isn't limited to new instruments, it also involves refining our existing theories. The current model of black hole accretion, while robust, may not yet account for all the complexities observed in this case. For example, the sudden shift from a feeding frenzy to a violent outburst could challenge existing assumptions about how energy is released during accretion. Some scientists are already exploring alternative models, such as the role of magnetic fields in regulating the flow of material into the black hole or the impact of turbulence in the accretion disk. These theories could be tested with future observations, potentially leading to a paradigm shift in our understanding of black hole behavior. Another area of focus is the study of feedback mechanisms between black holes and their host galaxies. The energy released during an outburst could influence the surrounding environment in ways that affect star formation and galaxy evolution. By observing how these processes unfold over time, astronomers might uncover new connections between black holes and the large-scale structure of the universe. This could have far-reaching implications, not just for astrophysics but also for our understanding of cosmic evolution. Yet, even with all these advancements, there are still mysteries that remain unsolved. For instance, the exact trigger for the outburst, whether it was a sudden change in the accretion disk, a collision with another object, or something entirely different, remains unclear. Future missions may need to address these questions by focusing on specific phenomena. For example, the next generation of X-ray observatories, such as the Lynx X-ray Observatory proposed for the 2030s, could provide high-resolution data on the extreme conditions near a black hole. These observations might reveal the presence of shock waves or other features that could explain the transition from feeding to outburst. Similarly, the development of more advanced spectroscopic techniques could allow astronomers to study the composition and motion of ejected material in greater detail, shedding light on the physical processes at work. In some cases, the answers might come not from new instruments, but from reinterpreting existing data. As astronomers refine their analysis techniques and develop more sophisticated models, they may find new patterns in the data that were previously overlooked. This could lead to unexpected discoveries, such as the identification of similar outbursts in other black holes or the detection of previously unknown phenomena associated with these events. The importance of these efforts extends beyond the study of individual black holes. Understanding the mechanisms behind these outbursts could have broader implications for fields such as astrophysics, cosmology, and even planetary science. For example, the energy released during an outburst could influence the surrounding environment in ways that affect the formation of stars or the distribution of elements in the galaxy. By studying these effects, scientists might gain insights into the role of black holes in shaping the universe on a cosmic scale. Moreover, the study of black hole outbursts could also inform our understanding of extreme physics. The conditions near a black hole, where gravity is so intense that it warps spacetime, provide a unique laboratory for testing the limits of our physical theories. Observations of these events could help scientists probe the nature of spacetime, the behavior of matter under extreme conditions, and even the potential existence of new physics beyond the standard model. However, the path to these discoveries is not without challenges. The vast distances involved in observing distant black holes mean that many of these events are rare and difficult to study. Additionally, the complexity of the phenomena involved requires interdisciplinary collaboration, bringing together experts in astrophysics, computational modeling, and observational techniques. This collaborative approach is essential for making progress, as no single instrument or method can provide a complete picture of these events. As we continue to push the boundaries of our observational capabilities, the study of black hole outbursts will remain a vibrant area of research. Each new discovery brings us closer to understanding the fundamental processes that govern the universe, while also raising new questions that will drive future exploration. The story of this particular black hole's feeding frenzy is just one chapter in a much larger narrative, one that will be written by the next generation of astronomers, using tools and techniques that we can only begin to imagine. In the end, the pursuit of knowledge about these cosmic phenomena is not just about answering questions, it's about expanding the horizons of human understanding, one observation at a time. Imagine a cosmic beast, a black hole, feasting on the remnants of a dying star. For millions of years, it's been slurping up gas, dust, and debris, creating a dazzling disk of superheated material that glows with the light of 1,000 suns. But now, astronomers have caught this black hole in the act of something extraordinary, a dramatic shift in its behavior that challenges our understanding of these enigmatic objects. What they witnessed wasn't just the end of a meal, but a violent expulsion of energy, a cosmic equivalent of indigestion. This event, observed through telescopes across the universe, offers a rare glimpse into the turbulent life of a black hole and the forces that govern its growth. Let's break down what happened, why it matters, and what it tells us about the universe's most powerful engines. First, the black hole's feeding frenzy. When a black hole accretes matter, it doesn't just swallow it whole. The material forms a swirling disk around the event horizon, heated to millions of degrees by friction and gravitational forces. This disk emits intense radiation, making the black hole visible even across vast cosmic distances. But this process isn't constant. Sometimes, the flow of material slows, and the disk dims. Until now, scientists thought these dimming events were simply pauses in the feast. But the recent observations reveal something more dramatic, a sudden, explosive shutdown. The black hole's disk didn't just fade, it erupted in a powerful outburst, sending shockwaves through the surrounding space. This isn't just a minor hiccup, it's a massive release of energy, comparable to the brightest explosions in the universe. So why did this happen? Theories are swirling, but one leading idea involves the black hole's magnetic fields. As the disk spirals inward, magnetic forces can become unstable, creating turbulence that disrupts the flow of material. This turbulence might have triggered a sudden surge of energy, expelling gas and radiation at near-light speeds. Alternatively, the collapse of the disk itself could have generated a massive burst of energy, a kind of cosmic belch. Either way, the event underscores how dynamic and unpredictable black holes can be. They're not just passive vacuum cleaners, they're active participants in the dance of cosmic matter, capable of both destruction and creation. The implications of this observation are profound. For years, scientists have debated how black holes regulate their growth. Do they feast continuously, or do they have cycles of feeding and starvation? This event suggests the latter. A black hole can abruptly halt its intake, releasing energy in the process. This behavior might help explain how supermassive black holes, which reside at the centers of galaxies, influence their surroundings. By expelling vast amounts of energy, they could shape the evolution of entire galaxies, preventing excessive star formation or triggering it in bursts. Understanding these cycles is key to unraveling the role black holes play in the universe's cosmic machinery. What's even more fascinating is how astronomers caught this event in real time. By combining data from multiple telescopes, they were able to track the black hole's behavior across different wavelengths of light, from radio waves to X-rays. This multi-wavelength approach revealed the full scale of the outburst, showing how energy was ejected in complex patterns. It's a reminder of how modern astronomy relies on collaboration and advanced technology to peer into the cosmos and witness these rare, high-energy events. But this discovery also raises new questions. How common are these outbursts? Are they a unique event, or part of a broader pattern in black hole behavior? And what happens after the outburst? Does the black hole resume its feeding, or does it enter a prolonged dormancy? These mysteries highlight the ongoing quest to understand black holes, which remain one of the most intriguing and mysterious objects in the universe. If you've enjoyed this deep dive into the cosmic drama of a black hole's feeding frenzy, consider subscribing to FactVerse for more stories like this. Every day, we explore the latest discoveries in space and science, unraveling the mysteries that shape our universe. And if you have your own theories or questions about black holes, cosmic outbursts, or anything else, drop them in the comments. The universe is full of wonders, and your curiosity is what drives us to keep exploring. Until next time, stay curious, and keep looking up.